Hello and hi students! Miss Nini here. So before I wrap up the video playlist now, I would like to share a story entitled The Intruder with you guys. Here is the online book I created as you can see. Now let us read this book together, shall we? The Intruder. A long time ago, there was a village deep in the jungle that was inhabited by bears and other animals. They all value each other. All the animals stay together and live in a very harmonious environment. On a peaceful evening, while the villagers are doing their own routine with their family and friends, suddenly they heard a loud noise from their east wall. All of a sudden, a gigantic monster appears out of nowhere and tries to invade their peaceful community. The children shout aloud as the scenario causes chaos. This has never occurred in their village before. All of the villagers ran for their life and some even made an attempt to tuck themselves away in the cave and holes. They are all trying to save their own life. Some villagers make an effort to alert others to seek refuge. At the same time, they also give signals to the soldiers to get ready for battle. The valiant soldiers are all prepared to fight and defend the village. The soldiers march down and take positions to attack the monster. The monster was shocked as he could see that the number of soldiers was large and that it could be easily defeated by them. The villagers come out of the shelter and join the soldiers to fight. When the brave soldiers are about to fight, the big monster screams and tries to run away for his life. Then a mighty king emerged from his tiny fortress. He warned the monster not to return to the tranquil village after seeing all the destruction it had caused. The honorable king reveals the law of the jungle to each and every villager as well as to the monster, when he made a point of saying that any intruders are subject to death. From the story and video before, what can you conclude? Yes, we can tell that in our daily life, there are a lot of laws that we have to obey. First, we can infer from Maya and her friends' driving scene that all drivers worldwide are required to follow traffic laws. Then, according to the intruder story that we have read just now, the monster has to obey jungle law. The same goes to our planets, which move around according to Kepler's law. I have a telepathic sense that there are thousands of questions lingering in your mind. You guys must be wondering, Kepler's law? What is that? And who is Kepler? And numerous others. No worries, my students. Let me explain to you this vital astronomical question. What are Kepler's law of planetary motion? But before we actually go and discuss today's topic, Kepler's law, here are our learning standards.
But first, make a guess. Know who is Kepler? How many laws? Draw a planet? Calculate the area?
At the end of this lesson, all of you, my lovely students, you will be able to first explain Kepler's law. Second, express Kepler's third law. Third, solve problems using Kepler's third law. Okay, students, before we proceed any further, I want to tell you a little bit of history, shall we? The book Astronomia Nova was released in 1609 by German astronomer, mathematician, and astrologist Johannes Kepler. Kepler published the results of his 10-year investigation on Mars motion in his book. After analyzing data gathered by Tycho Brahe for years, Kepler developed 3 planetary motion equations that contradicted to previous hypotheses about how planets revolve in our solar system. Amazing, right? Moving on to Kepler's law. However, there are a few fundamentals regarding the geometry of an ellipse that you should be aware of before we go into the laws. An ellipse has two axes, the main axis, which is the longest, and the minor axis, which is the shortest. It has two foci, which is the plural of the focus, which are its focal points. The foci are always evenly distributed on either side of the center and are located on the main or longest axis. In addition, more than half of the solar system's planets have nearly elliptical orbits. Considering this, why are we studying ellipses? That is because Kepler's first law, the law of orbits, states that all planets move in elliptical orbits with the Sun at one of their two foci. In other words, Kepler's genius was in realizing that rather than traveling in perfect circles, the planets actually follow elliptical routes during a rotation, with the Sun situated at one of primary axis foci. Because of this, the elliptical orbits of the planets in the solar system nearly entirely have a round form. The average value of the distance between the planet and the Sun is also represented by the orbit is radius. Isn't it easy, my students? Done with Kepler's first law. Now let us see the second law of Kepler. Imagine a line appearing from the Sun and joining a planet Earth. This line is called the radius vector. Let us now imagine that the Earth moved in a specific amount of time from position P1 to position P2. The radius vector's position has now changed along with the planets, and its movement now has spanned an area that we refer to as A1. Now, let us move the Earth to the other side, where it moved from position P3 to position P4 in the same length of time given by the letter T. E2 represents the area that the radius vector covers. Aha, students! Now we have come to the interesting part. I guarantee that you will be surprised to know. Drum roll down. According to the Kepler's second law, the area of A1 will be equal to the area of A2. Wow! How could it be? Yes, the second law, the law of area, states that a line that connects a planet to the Sun sweeps out equal areas at equal time. In other words, the planet moves faster when it is closer to the Sun and slower when it's further from the Sun. This is due to the fact that the linear speed from P3 to P4 is faster compared to the one from P1 to P2. Impressive! Students, we have reached the last law of Kepler, commonly known as the law of periods. It can be said that any planet's orbital radius is directly proportionate to the cube of its square orbital period. It compares the orbital period and radius of the planet's orbit to those of other planets. Plus, the ratio of the squares of the periods to the cubes of their average distance from the Sun is the same for all of the planets. This table shows how each planet compares to the others. What does that mean exactly? According to Kepler's third law, a planet's period is when the amount of time it takes it to orbit the Sun it relates to its mean distance from the Sun, proving that the time it takes a planet to orbit the Sun increases significantly as its distance from the Sun increases. In other words, a constant is equal to the square of the period divided by the cube of the mean distance. And that is all. The square divided by r cube is the same number no matter the period or distance. Easy marks for you all right here. Now that we have done with all the theories, should we learn about how to express Kepler's law and solve problems using Kepler's third law? Let's go. Kepler's third law can be derived using Newton's universal law of gravitation and the concept of circular motion. Assume that the orbit of the planet around the Sun is a circle as shown. When a planet moves in an orbit around the Sun with velocity v, the centripetal force is caused by the gravitational force. Then, centripetal force equal to gravitational force. We write it down mv squared divided by r as a. So, the velocity of the planet is given as v equal to 2r divided by t. So, we put this as a b. Where t is the orbital period, we substitute b into a, where k is a 42 divided by gm is a constant. Therefore, t squared is directly proportional to r cubed. To solve problems involving Kepler's third law, we can use the proportion method. Since t squared is divided by r cubed is equal to k, we can use the proportion, where t is the orbital period and r is the orbital radius. Remember, students, the equation involves the period of orbit of one planet divided by the period of orbit of another planet. The same units must be used for both periods. SI units need not be used. Everything is in your heads already. Now, let us do some exercises together. Question number 1. Diagram 1 shows a planet revolving around the Sun. O is at the center of the Sun. The time taken for the planet to move from P to Q and from R to S are equal. Which statement is true? A. The area of POQ is equal to the area of ROS. B. The speed of the planet orbiting the Sun is uniform at all points in the orbit. C. The planet is moving at a higher speed from P to Q compared with from R to S. D. There is no gravitational pull between the planet and the Sun when the planet is at P. The correct answer is A. Next, question number 2. All planets move in elliptical orbits with the Sun at one focus. Which law does the above statement refer to? A. Newton's universal law of gravitation. B. Newton's first law. C. Kepler's second law. D. Kepler's first law. Correct! D is the answer. Last objective question, class. Number 3. Which statement explains Kepler's second law? A. The planetary orbits are elliptical with the Sun at one focus. B. The radius from the Sun to a planet sweeps out equal areas in equal times. C. The radius of orbit is the average value of the distance between the planet and the Sun. D. The farther a planet from the Sun, the longer the time to complete one orbit around the Sun. Come on, students. I hope you guys can guess the answer correctly. Yes, B it is. Alright, so we have done answering the objective questions. Now, let us practice calculations together. Okay, class, so I have my calculator right here. Don't forget to get yours. And now, let us solve these problems together. So for question number 1, if Saturn is on average 9 times farther from the Sun than the Earth is, how long is its orbital period in terms of Earth years? Now, Kepler's third law states that the proportion of period square divided by the distance from the star cube is equal for all the planets. It's same for all the planets. Okay, and then so this is how the formula turns out. Sorry, like this. Okay, so this will equal the same radiation for that of another planet orbiting the same star. Okay, now plugging dummy variables, assuming since we are trying to find our answer in terms of Earth years, we are going to substitute 1 for T1 and for R1 like this. Okay, because this is giving us its saying 9 times farther from the sun than the Earth is. So we are going to set this equal to our information for Saturn now. So we are solving for the period we don't know. So I will put the S, and our radius is 9 times farther. Sorry, 9 times farther. Okay, don't forget to put this cube and square. And then once we go ahead and solve the problems like this, we will get the answer. Okay, faster. Who will get the answer first? 297. So it gave you an answer of 27. So it's 27 Earth years, class. That is how a long year for Saturn is. So that's it. We got the final answer. You got it, class? Okay. Now that we have done all the exercises together, I hope that all of you, my lovely students, are able to check off the list. In conclusion, Kepler's laws of planetary motion reveal the nature of planetary orbits, the relationship between distance and orbital speed, and the predictive power of orbital dynamics. These laws support the heliocentric model, which places the Sun at the center and planets in orbit around it. They also establish proportional relationships between orbital period and average distance, indicating that the farther a planet is from the Sun, the longer its orbital period. Additionally, Kepler's laws enable predictions about planets' behavior, allowing us to estimate their orbital periods and mass. These laws provide valuable insights into the behavior of celestial objects in our solar system and beyond. Remember, class, to have better memorization and skills, keep practicing, okay? As your homework, you can do exercises in the textbook. Well done for today's class, and thank you. I will see you in the next class. Bye!